Okay. I'll wait for 2 minutes for everyone to join, and then we'll start with the lecture. Okay, I suppose most of you have joined now. So let us start with the lecture. So in the previous lecture, as per the discussion that we had is, we started our discussion with the backpropagation algorithm that is being used in the case of multi-layer perceptron. So our main idea in the case of multi-layer perceptron was, we discussed there are two main passes in the case of multi-layer perceptron. One is forward pass, which is feed forward, or in some textbooks you may also come across feed forward process or forward propagation. And the second part is the backward propagation, which is mainly which is the second part in the case of multi-layer perceptron. So what is the process in the case of feed forward, that is forward propagation, is you will be having certain input which will be passed through the input layer, through the hidden layer, and the output will be generated through the model that you have created, and error will be calculated. Later, in the backward propagation, this error that you have calculated will be used to update your weights in order to reduce the loss that you are facing in the case of multi-layer perceptron, the loss that you are encountering while for the data set that you have created for the input that you are passing, right? So we this is the main idea, and in the case of back propagation, this error that we have calculated in the output layer is being propagated backwards, so that we can also obtain the error. We can also update the weights that is present in the connection from input layer to hidden layer, right? So we also saw that in the case of hidden layer, we do not have any explicit error because we do not have any output. We do not have any yes, right now I haven't shared the screen as of yet. Uh, okay, fine. I'll share the screen in a short while. But, anyways, so So I was at the point that in the case of multi-layer perceptron, we also saw that in the case of hidden layer, there won't be any explicit error that we will be able to calculate, because there won't be any target output associated with the hidden layer. As such, in the case of output layer, we have a target output associated with the output layer. That's why we are able to calculate the error that is being generated in the output layer. But in the case of hidden layer, there is no explicit output uh, uh, that is determined. That's why what we'll be doing in order to update the weights associated with the hidden layer connections, will be passing the error backwards. That is, we'll be propagating the error backwards till the initial layers that we have. Okay. So after this, we also studied about the derivation part. We went through an example for the derivation. That is one of the examples that I uh, uh, that I showed you for the derivation process. And later on, the what is being given in your reference book, that is the Tom Mitchell book, the generalized form of derivation in the case of a multi-layer perceptron, that we went through. So in the case of, just a minute. So I hope that you all have gone through the PPT that I uploaded on Wednesday. I suppose that you all have gone through the PPT, yes or no? Did you study the PPT? Anybody is facing any difficulty while going through the PPT? Okay. All right. I suppose that I expect some acknowledgement in the message section, whether you have gone through the PPT or not, or if you are facing any difficulty while you went through the PPT, yes or no. All right. I suppose you must have. Anyways, so let us proceed. So our discussion in the previous lecture ended here, where we discussed, where we were talking about two of the cases, that is input layer, where the gradient descent for the case of input layer and gradient descent for the case of output layer. So we already discussed, hidden layer, and in the case of output layer. So we already discussed the training rule for the output unit weights. That is the same chain rule that we have implemented in the case of the example that we discussed. The same chain rule is being implemented over here as well. Only the case is that here the different notation is being used. I suppose that the notation is not the problem here, right? Because the chain rule actually means the same. What we had discussed in the case of multi-layer perceptron that we created previously, which was of one hidden layer. There was one hidden layer in our multi-layer perceptron and one output layer in our multi-layer perceptron. So and we were talking about in the case of here, the net j that they are talking about is actually the z value that we were calculating. That is a weighted sum that we were calculating, and we were mentioning p hat as our output, and here oj is mentioned as our as the output value over here, right? And the chain rule that is being signified over here is similar to that we had discussed previously. That is the error with respect to the z value, that is the weighted sum value, can be presented in the form of a chain rule, because the error, the output, the z value will impact your output value, and output value will eventually impact your error value, right? So this is a chain rule. And also the error also we have defined, which is the difference. The MSE loss function is our error in this case. So it is a difference between the actual output and the predicted output, where OK is a predicted output of your model, right? And also this is the derivation that is being performed here. I suppose need not go in the depth of the derivation, because you already know, and we had already performed the derivation in that case, in the example case, right? And also the derivation of the sigmoid function with respect to OJ. And you also know that derivation of sigmoid function with respect to x will be sigmoid into 1 minus sigmoid, right? That is the derivation that we have. And so is the output here, right? In the case of our example, we had p hat into 1 minus p hat. And since p hat is being mentioned as OJ over here, so it is OJ into 1 minus OJ, right? So this is the value of the error, the gradient value that you are getting in the case of a training rule for the output layer. So we will be having two training rules, one training rule for the output layer and one training rule for the hidden layer. Why different training rules for both the cases? Because in the case of output layer, we have directly error associated with the output layer. So we can directly calculate the gradient value using a normal chain rule that we have. But we had already discussed, yes, there is no error associated with the hidden layer. That's why we need to perform a certain back propagation. That is, we have to propagate the values that are present in the output layer back to the hidden layer in order to calculate the training rule, in order to obtain the training rule for the hidden layer units, right? So I suppose this is clear, right? So we have the value of del ED upon del net J. And so from that, we can calculate the value of the gradient value. The total gradient value can be calculated over here. And this value you have to add in the weight update rule. So your weight update rule will be something like this. W new is equals to W old minus alpha into del ED upon del WJI, whatever weight that you are trying to update. So here, this whole thing is being mentioned as del W. Okay, del W, this along with the minus sign. This whole thing is mentioned here as del W, which is actually this one. This is your value that you have calculated, and this you can use to update your weights. So here we have different notation WJI, and this values can be different for different I and J values, right? That you might be able to understand as of now, right? So for different connection, this I and J value will be keep on changing, and you can find the value of the weight update rule for each of the connections that you have with the output layer, right? After this, next training rule that we have is a training rule associated with the hidden layer, right? So training rule associated with the hidden layer, in this case, what we are doing is, we are actually the del ED, the value of del ED by del net J will be actually the summation of all the K that belongs to downstream. What does downstream mean? Downstream means here is the connection from node J, which are immediate downstream of node J in the network. So the input to the immediate connection of node J means the hidden layer is here. Okay, these are the hidden layers that we have in our connection. These are the hidden layer that we have in our multi-layer perceptron. So all the downstream of this particular hidden layer, for example, if we are calculating the weight associated with this connection, then all the downstream of this particular node J will be this particular output node. Okay, this particular output node. Suppose we have multiple output nodes. In that case, all the connections. So here, this one will also be considered in the downstream. Again, if we have one more node in the output layer, this node will also be considered in the downstream. So summation of all this value will be impacting the error value of the hidden layer. Yes or no? Are you getting the point? Why this notation is being presented here in this form? Yes or no? Right? Right? Okay, so that's why this K belongs to downstream actually means that those nodes whose direct input is the output of this particular node. So this hidden layer, those nodes whose input is the output of this particular node, this node that I'm talking about. The output of this node will be input of these all nodes, right? So these are all the downstream nodes of this particular node. So all the errors, all the gradient value that is being calculated here will ultimately impact the value, the error value that you will be calculating at this particular hidden node. That's why we have the error, the gradient value is actually the summation of all the downstream values that are present, that are all the downstream nodes that are present for this particular node, right? So it is actually ultimately del ed upon net k into net k upon del net j. Yes, yes, right. In softmax there is multiple downstream. Yes, that is correct. In the case of softmax, also you may have in the case of linear regression as well, if you see. Yes, means node of output layer that are connected to nodes of hidden layer, right? Nodes of the output layer that are connected to that particular hidden layer. So in this particular notation, this hidden unit is connected to how though all the output nodes that are connected to this hidden node, that all will be considered as the downstream. Are you getting the point? Okay. And Prince, there is a possibility that you may have multiple outputs in the case of regression as well. If you recall that we had discussed in the case of multiple in the regression, in a linear regression also, you can have multiple outputs in the linear regression also, right? For example, with the same data set, we may be calculating the house price prediction as well as some other thing regarding number of rooms in a particular house. Okay, two of the outputs can also be there in the case of regression also. So you may have in the softmax, in the case of regression also, you may have multiple outputs, right? Okay, I suppose that is clear, right? This is not explicit to the softmax only, right? Okay. So K belongs to downstream, that is this particular nodes that are present in the output will impact the hidden layer output, hidden layer error. So these all will be considered when you are calculating your gradient value for the hidden unit, right? So ultimately this K actually mentions the output. K actually mentions the output node that you have. These all node will be mentioned by K, and so we have will be passing in the backward. If you see, will be going in the backward form. So ultimately, it will be del ed upon del net K into del net K upon del net J. If you are not able to visualize this, then you recall that in the case of output, we had Z2 as the output, where W1, let us see, W1 to H1 plus W2 to H2 was the Z2 output, which is actually net, you can call net K output that we have. And in the case of net J, that is Z11. If you see, so ultimately, if you are making any changes in the case of Z2, ultimately it will impact, net K is actually, now let us go with the net J output. Net J output means what? Hidden layer output. So hidden layer output, if you recall, we had two outputs that we had discussed. Let's go through the example. Let us go to the example part. Okay, in this particular PPT, if you recall, we had Z11. So here we have a particular output, net J output. Here we have a particular sum, weighted sum. Here we have a particular weighted sum. So this is the value that we will be getting here, which is ultimately H1 value. If you apply a sigmoid to this particular, this will be your H1 value that will be getting as an output. So you can say that any change that you make in the case of, let us go to this. Any change that you make in the case of Z111 will ultimately impact your H1, and this will ultimately impact your Z2. Now, are you able to see this particular? Are you able to visualize this? So net, yes, H1 is actually the net J. Yes, net K is actually the output. K is actually the output node, and net J is actually your Z2 value. Net J is actually your output in the hidden layer output. So ultimately, if you apply the sigmoid to the net J, that is your H1. Are you getting the point? Sigmoid to your net J will be your H1. Yes or no? Yes, H1 is the output of the hidden layer, right? H1 is the output of the hidden layer. Okay. Are you getting this chain rule now? Yes or no? Because of the notation, you might be getting confused. That's why I related to the example that we had discussed previously. So now are you able to understand what is net K and net J? Net J is actually the hidden layer output that we have, hidden layer weighted sum that we have, and net K is the output in the output layer that we are using to obtain the gradient value in the hidden layer, right? I suppose that is clear. And so these are the derivations. Following will be the derivation part. After this, there is a derivation part that we have. So these are all the derivation part. I suppose that must be clear. That is ED, del ED upon del net K. This is already calculated previously. We have already calculated in the case of output layer. We have already calculated. That's why it is directly mentioned as delta K. Okay, so in that case, this particular value was denoted, this particular eta Tj minus Oj into Oj into 1 minus Oj was mentioned as del J. So this was actually calculated in the case of output layer, which is written as del K over here. Okay, so if you go through the derivation once again, you will understand that this particular part, del Ed upon net K, which we have already calculated. This, if you recall, this we have already calculated in the output layer. Since it is the derivation of error with respect to the output in the output layer, this we have already calculated in the case of output layer. That's why they are directly mentioning it as del K. Are you getting? I suppose that is not a problem here, right? Yes. And so we are remaining to calculate only this part. That is del net K upon del net J. Okay, only this part is remaining. And we can say that del net J will impact our OJ value, that is the output value. And ultimately that will impact our del net K value. And we can say that del net K is actually your summation, that is weight into W12 or into OJ, that is output from the hidden layer is here. Is it the weighted sum of output from the hidden layer and the weight associated with the that particular part. So we can, if you perform the derivation, the weight will be your output. If you perform the derivation with respect to OJ of this particular part, the weight will be the output. Hence, here WKJ is the output for this particular derivation. Okay, I'm giving you 2 minutes to go through this derivation once. Just let me know that if you are facing any difficulty in the derivation part, if any of the derivation part, just let me know, because I need to know that you are clear with this whole thing. Okay, I suppose, is everything clear up to this? So this is a downstream and this is the del K value that we had calculated previously in the output layer. This derivation part is being simplified over here. This derivation part is being simplified, that is being calculated over here in this particular portion that you are mentioning, that is mentioned to you. Any doubt up to this? Any doubt in the derivation part? If you are facing any difficulty in the derivation part, what I would suggest is go through the example that we had discussed and try to relate with that example. You will be able to understand in a much simpler manner. Rather than going to the direct notation, it will be much simpler to go through the example and come back and go through the derivation once. Are you getting the point here? So I suppose, need I go through the derivation once, or it is clear? Okay. Okay, so this will be the output that you'll be getting. That is the derivation output that you'll be getting in the case of the hidden layer. And ultimately, you will be getting a weight update rule for the hidden layer as well. Okay, you will be getting a weight update rule for the hidden layer as well. So this is the weight update rule that we are getting for the hidden layer, right? And this downstream summation will be the sum of all the connections that we have from hidden layer to the output layer. Okay, all the connections that we have from the hidden layer to the output layer. I suppose this is clear. That is the second case that we have. That is a training rule for hidden unit weights that is being associated. That is, we'll be updating the hidden layer weight update. Okay, so ultimately your back propagation algorithm, your final back propagation algorithm that is given to you is of this form. Okay, we have two errors that we have a way for output layer, that is a del k, and for hidden layer that is a del k value for hidden layer and del k value for the output layer, and these are the values that we are having. And also go to the notation where OK is the output that is being generated for this particular unit. For example, in a particular output unit you would be having a particular output that is being generated for this particular unit. That is the way the sigmoid value that you'll be generating, right? And this is the weight update rule. Since we have already performed, if you recall, wij was minus alpha into del ed upon del wij. That's why here plus is mentioned. Otherwise, if you recall, in the case of linear regression, when we had seen for the gradient descent rule, our weight update rule was theta j is equal to theta j minus alpha into del j upon del theta. So this whole thing they have taken as del wj, and so here there is a plus sign. So don't get confused in that case, right? And we had seen that del wji is equals to eta into del j into xji. That is the input value. Okay, input value that you have, and del j we have calculated based on the derivation that we have performed. Okay, I suppose the whole backpropagation algorithm and the main idea behind the backpropagation algorithm is clear to everyone. Yes or no? Okay. Okay. So now I'll be giving you an example to solve, wherein first thing that you have to do. So you are given an example here. Just a minute. I would also like to share this particular PPT. Okay, you have the PPT, right? So you can, from the PPT, you can go through the backpropagation algorithm that is given to you. So what you're supposed to do is, for this particular example that is given to you, this calculation-based example, first what I expect is find me the output that is being generated at O5. Okay, find me the output that is being generated at O5 based on this weights and the inputs that is given to you. So you are given from the connection, from the input, you are given two inputs, that is x1 and x2, two inputs are given to you. And with each connection, you have a weight associated with each connection. So first of all, what will be the output for H3? That is the hidden layer 1, hidden layer unit 1, output for H4, and the final output O5. Okay, so I'm giving you 5 minutes to calculate what is the output that is being generated at O5. Just let me know what is being the output that you are generating at O5 and H3 and H4. Okay. Okay, anyone done with the calculation for H3? Just for H3. Output that is being generated at H3. Okay. Okay. 0.587. Okay. And H4 is getting is 0.56. I suppose that you all have performed the calculation properly, right? So for the case of H3, first we'll be calculating weighted sum. Weighted sum that is being calculated over here will be the sum of X1 into the weight associated with this W1 plus X2 weight associated with W23, that is 0.8. So what is the output that you are getting over this point? At this weighted sum value, what you are getting? 0.355. Okay. That is the value that you are getting at the weighted sum. Okay. So based on that, first you will be calculating the weighted sum. That is here you will be getting as 0.355. Everyone is getting 0.355 as the output here. Later, to calculate the output generated at H3, what you have to do is perform the sigmoid of 0.355, right? Sigmoid of this. So this output that you are getting as is 0.593, right? That is 0.593. Okay. Is it clear to everyone how we are performing the calculation? Anybody is having any doubt? Okay. Similarly, give me the result for H5, H4. What is the output that you have generated at H4? Okay, H3 is 0.587. H3 is 0.587. Somebody is saying 0.587 and someone is saying 0.593. So I'll cross check and let you know. But calculate at H4, what is the output that is being generated? And I suppose that what is the output that is being generated at H5 is clear, right? How will be calculating for the output at H5? That is the weighted sum of H3 into W35 plus H4 into W45. And the sigmoid of this will be the output of the O5. Sigmoid of Z will be the output of O5, right? Okay. H4 and weight equal to 0.38. Weight is 0.38. Okay, H4 is 0.593. Fine. Just calculate for O5, that is output. Okay, H4 is 0.593. What is the output that is being generated? Anybody is having any doubt in the calculation? Just let me know in the comment section or through by unmuting yourself if you are facing any difficulty. Do not hesitate to ask any question in the classroom. Just let me know, right? Okay, yes, I'll repeat the formula for the output. So formula for the output, as we saw in the case of H3 also, what we were doing, we were performing the weighted sum of the inputs and the weight associated with the connection. And then we were generating a weighted sum and performing the sigmoid. In the case of output also, what will be the input to the output layer? The input will be the output that is being generated in the hidden layer will be the input to the output layer, right? So H3 and H4 will be the input in the case of output layer, right? In the case of output layer. Hence our weighted sum formula will be something like this: H3 into the weight associated with this connection, that is W35, plus H4 into the weight associated with the connection that we are having from the hidden layer to the output layer, that is W45. This is the weighted sum value that we'll be getting, and later the sigmoid of this particular Z will be the output that is being generated at O5. Are you getting now? Yes, this is the downstream. No, yes, this is one way the downstream. No. Right now we are performing forward propagation only. Okay, when we are performing downstream, when you will be performing downstream, at that point of time, what will be multiplying? We will be performing the product of the. If you recall the formula also, if you recall the whole derivation part also, what we'll be doing is this del k. This first you will be having an output that is being generated at hidden layer. And what you'll be doing is you will be performing the product of weight and the error that is being generated at output layer. Error that is being generated at output layer means the del k value that you are generating. How we'll be calculating the del k value in the output layer? We have the formula for output layer as well. Okay, we have the formula for output layer as well. Yes, calculate the error term, which is the output into 1 minus output into the actual output into the predicted output. Okay, are you getting the product? The sum of this, that is the error that is being generated over this output, and the weighted and the product of this weight will be the downstream value. Are you getting that? Yes or no? Okay. First, calculate the output that is being generated. First, let me know what is the output that you are generating here based on forward propagation. Okay, 0.67 is the output. Okay, 0.67 is the output. Fine. Now, what we are supposed to do is perform the back propagation process. Okay, now what we are supposed to do is back propagation. So first what we'll be doing is, if you recall, we have two formulas that is being given to you in the back propagation algorithm. First is for output layer and another is for hidden layer. Okay, so for output layer, we have something like this. Del J is equals to OJ into 1 minus OJ into TJ minus OJ. Tj minus Oj, where Tj is the actual target value, and Oj is the output that is generated by the model, generated by the multi-layer perceptron. Okay, so we have Oj value with us, which is 0.67, and Tj, suppose I am saying that 0.5 is the output, target output value that is supposed to have, that you are supposed to have. So what is the del J value? That is the error value that you will be generating in the output layer. What is the error value that you will be generating in the output layer, in the output unit? Just calculate the error that you will be generating in the output unit and let me know. Okay, what is the value of Tj? Tj is 0.5. Tj is 0.5. Yes, 0.00 minus 0.0037. Yes. This is the value. This is the del phi value. Okay, just consider this is the del phi value. That is the error associated with output unit. Okay. Now we have error associated with output unit. Now can we calculate the error associated with the hidden unit? Error associated with hidden unit, can we calculate now? Okay, we have del phi value which is minus 0.037. So now what is the error in the case of hidden layer? Just go through the formula that is given to you. Error associated with hidden layer is, for example, let us calculate with the help of for del 3. For del 3, your error associated with hidden layer is something like this, which is of is Oj into 1 minus Oj into a summation over K del K W Kj. Okay, where del K, this whole thing is for the output layer, all the downstream that you have, all the downstream that you have from this particular particular hidden unit, all the downstream that you have from the particular hidden unit. So only one downstream we have from the particular hidden unit. If you see the multilayer perceptron, how many downstream that do we have in the case of H3? How many downstream do we have in the case of H3? Only one downstream we have, which is the connection from H3 to O5, right? So what will be the value here? So you can say del 3 is equals to the output that is being generated at O3, 1 minus O3, into the weight associated with this connection, weight associated with W35, W35 weight into the output, the error that is generated in the output layer. Okay. So what is the value? Are you getting the formula? Is the formula clear to you? Yes or no? Yes, O3 means H3. Yes, yes. O3 means I just mean that output that is generated at H3. Okay. You have already calculated the output that is being generated at H3, the sigmoid value that you had calculated, right? So are you getting this whole formula is clear to you or not? Everyone is clear with this particular formula for calculating the error associated with the hidden layer? Okay. What about others? Tell me what is the value of del 3? Okay. Keval is getting minus 0.0112 as an output. Okay. For this error value. Are others getting similar value? Okay. Right. Okay, fine. So similar to del 3, now can you tell me what will be the del 4? Which will be O4 into 1 minus O4 into the connection weight, that is W4 phi into del phi. Yes or no? Yes or no? Which is the connection weight from this particular hidden unit, this particular H4 hidden unit to the output unit. Yes? So this is the error for del 4. That is the error that is being calculated at the H4 unit. This formula, are you getting this formula or not? Yes or no? Okay. Fine. So similarly, you can calculate for del 4 now, right? So after calculating this delta error values, what we have to do is we can calculate the weight update. Okay, weight update. Fine. So Keval has calculated for del 4 also, which is 0.0814. I suppose others, what about others? Others are getting similar value? Okay. Now that you have the error, you have the error associated values. So can you calculate the W4 phi new? Okay, updated weight for this particular connection. Updated weight for this particular connection, W4 phi. So it will be, if you see the backpropagation algorithm that we had discussed already, which is the weight update rule is WJI is WJI plus del WJI. And del WJI is eta into del J into XJI. XJI is the input value, del J is the error value that is being calculated at that particular unit, and eta is your learning rate. Okay, eta is your learning rate. So here, what will be the value? W45 new will be equals to W45 old plus eta into the del phi value, that is the error that is generated at the output layer, and the xji, that is the input to the output layer. What is the input to the output layer? Y4. You may say Y4 is the input. Y4 from that particular from that particular node. From that particular node, what is the input? Y4 is a particular input, yes or no? From that particular unit only I'm talking about. From H4 unit, what is the input? H4, Y4 is the input. So what is the value that you're getting? Take eta is equals to 1. Now, and W45 old is actually your 0.9. Okay. So, W45 new is equals to 0.9 plus eta, that is 1, into del phi value that you had calculated was Y4. In this case, Y4, since we are trying to calculate, since we are trying to update the weight associated with this connection. Okay, W45 connection we are trying to update. So for this particular, what is the input that is given to the output unit from this particular connection? What is the input that you are giving? H4 is the input that you are giving to the O5. Yes or no? H4. And Y4 here means the same, sorry, Y4. So you are getting confused with the notation here, I guess. By Y4, actually, I mean H4 only. Okay, H4, if I mistakenly say Y4, that is H4. That is the output that is being generated at H4, right? Okay, Priya? Yes. Okay, so it is 1 into the del phi value that was generated was, I guess, minus 0.37, I guess, right? Yes, minus 0.037 and into the input, that is H4 value that you have calculated already. I suppose it was somewhere 593 or something. So now you can calculate what is the new weight associated with that particular connection. Yes or no? Okay, I am not aware that whether what is the del phi value. I just randomly took this value actually. I do not recall what is the del phi value that you had calculated. Do you have the record of what is the del phi value? Okay. No, that should not be del 4 actually. According to the formula, it should be del phi. Since we are trying to calculate, see, when you have the connection associated with this particular connection, there will be del 4. But we are trying to calculate for this particular connection. Okay, this particular connection. That's why we are taking del phi value. Are you getting the point? Okay. See, we are trying to update the weight associated del WJI, that is a connection from jth unit to output unit. That is this particular connection. Okay, this particular connection that is from H4 to O5. We are trying to calculate that what is the value of this particular, what is the value, what is the weight update rule that will be having in this particular case, right? So if you are taking the connection from a hidden layer to the output layer, we'll be taking the error associated with the output layer. Okay, so if you recall, we had different values of error associated. We had seen two training rules, for the training rule for the hidden layer and training rule for the output layer. In each case, we had two different del k values. Yes or no? from the network output K, we had calculated an error term, and for network for hidden layer, we had calculated an error term. For both of this, we had calculated error term, and for how we calculated the error term. Since we knew that for the connection from hidden layer to the output layer, we have an error associated with it. Then hence we can calculate directly. We can calculate through the chain rule. That's why we calculated del K. And from the hidden units to the input unit, from the input to the hidden unit, we do not have any error associated with that. So we propagated that error backwards. The error we had calculated from the output to the from hidden to output, that error we had propagated backwards. So this error, whenever we are trying to calculate, for example, if you are calculating for this particular weight update rule, in that case, this particular weight will be added in the calculation for this particular error. Okay, so in this particular case, we'll be using del phi only. Are you getting the point through the calculation also? Are you getting the point? Now is it clear why we are using del phi here? Because it is an error associated with the output unit, and we have yes, I suppose now it is clear. Yes or no? Okay, 0.8780. Fine. That is the value that you are getting for the output, for the new weight. Okay. Yes, approximately that is correct. 8780. So similarly, you can calculate the weights for hidden unit as well, for any hidden unit as well. And don't get confused here with the hidden unit and the output unit. So now if I ask you to calculate the weight update rule for W24, then it will be W24 old plus alpha eta into the error associated with this particular node, that is del 4. Okay. Just a minute. Del 4 into, and we have already calculated del 4, which is O4 into 1 minus O4 into W45 into del 5. All the errors that are going to impact all the output unit that is being impacted by that particular hidden unit, that all downstream values that we have already multiplied, right? So as a part of your homework, I'll be giving this particular exercise. What you have to do is try to calculate the weight update rule for hidden unit connections that we have, and let me know that whether you are getting the whole concept or not. So I suppose that theoretically you are clear with what is back propagation trying to do here. Yes, you can have 2 units at the output layer. At this particular point, we have used only 1 unit at the output layer. Okay, maybe we'll go through particular, but I suppose we can have more than 1 unit at the output layer that we have that we are clear with, right? We can have more than 1 nodes. For example, if you have a linear regression based problem also, you can have more than 1 unit at the output. 1 unit may be, yes, into x2, right. So for the connection here, input will be x2 over here, right? So that's why we'll be using x2, right? So try to calculate this particular values for all the connections that we have and weight update rules. But and let me know in the next lecture whether you are clear with the point or not. So I suppose up to this everyone is clear. This whole idea, the main theoretical point is clear to everyone. Yes or no? Okay. So in the next lecture onwards, we'll be getting a brief with the calculation. With the calculation, we might be getting a brief with the calculation. And from the next lecture onwards, we'll be starting with another classification algorithm that we have. The one more classification algorithm that we have is support vector machine. In support vector machine, we'll be talking about how this is also a, if you see, a support vector machine will also be your, we'll be talking about 2 types of support machine over here, linear classification and non-linear based support vector machine. Both we'll be discussing. And in the linear part, we'll be talking about a hyperplane that will be separating our both of these classes. So in this first, we'll be talking about binary classification in the case of support vector machine. In that, we'll be talking about how in hyperplane will be separating. You'll be utilizing the hyperplane to separate your both of the class input. So in the case of logistic regression, if you recall, we were trying to create a decision boundary in such a way that if you recall, in the case of binary logistic regression, we were utilizing sigmoid function. But ultimately, what we were trying to do in the case of sigmoid function also, we had weighted sum. And above this particular value, about this particular hyperplane that we had discussed, all the values will be positive, and below it, all the values will be negative. Something like that we had discussed in the case of logistic regression. If you recall a brief idea of it, yes or no? Yes. But we'll be discussing in brief, in detail in the support vector machine as well, that we'll be generating in hyperplane to separate this, and this hyperplane will be generated in such a form. We can have multiple hyperplanes, but we'll be generating a hyperplane in such a form that the margin that is being generated, margin is the distance of the particular point from the hyperplane, distance of the positive. For example, we have positive set of points, we have negative set of points, and margin will be something like this. So here, if you see, if you have a data set like this, so suppose this is a positive data, this is a negative data, and this from this point to this point, and from this point to this point, the first initial point, that is nearest point to this hyperplane, and nearest point to this hyperplane, from positive side and nearest point from the negative side, this margin should be maximum. Something like this we have in the case of support vector machine. And we'll be also going through some calculation based problems, such as we'll be calculating dual form of support vector machine and primal form of support vector machine. That also we'll be discussing. So one thing I want you to go through in before we go through the mathematical part is Lagrange multiplier. So everyone is aware about Lagrange multiplier? Yes or no? Is everyone aware of Lagrange multiplier in mathematics? If yes or no, just let me know in the comment section, in the message, in the. If you're not aware of it, I would suggest that you go through it once before we proceed with the SVM theory. A Lagrange multiplier is one thing. Okay, you are not remembering it at this point of time, it's fine. But this is a prerequisite before we proceed with the support vector machine, that you go through Lagrange multiplier once, so that whenever we perform the mathematical form of primal and dual form of support vector machine, you will understand what is going on. Okay. Fine, we'll also discuss in the classroom, but just I want to make you aware that this particular point you need to be clear with before we proceed with this, right? So this we'll be discussing from the upcoming lecture. We'll go through the mathematical part of this backpropagation once a little bit, and then later on we'll proceed with support vector machine, right? So, and also with the case of evaluation 1, at this point of time, I'm expecting that you all are aware that you have to upload your GitHub repository link in the evaluation 1. 27 of the students haven't uploaded yet. So of all these 27 students, I have noted the numbers, and for them, the evaluation will be considered with this also, right? So since you are not uploading your GitHub repository link, based on that only your evaluation marks will be good. So make sure that you were supposed to upload it by Saturday. By previously, I had given you with the time of Saturday, and this now next Saturday is going to come. So make sure that you have uploaded at least in the classroom. Take the instructions seriously, and I'll also see in your GitHub repository that what is the timeline that you have uploaded your work. So it is not that you upload just now and then you share your GitHub repository. I have noted down some special cases wherein you have faced certain difficulty with the commit and all. That all thing have been recorded, but others, I suppose that it should be uploaded by 2 months or 3 months ago. Okay, I'll take that things into consideration while taking the evaluation. So make sure that you have uploaded your GitHub repository link in the evaluation section, so that I can go through that what is the record of your submission so far. And also based on regarding the evaluation, maybe tomorrow may not be your evaluation, the Viva based evaluation for now, but be ready with your work, right? Be ready with your work and keep updating your repositories time to time. So I suppose everyone is clear. Okay, no, tomorrow we may not have evaluation. Tomorrow there is no, but I'll be taking your offline evaluation. That is, I'll be going through your work, what you have submitted, and later on I'll let you know whether you have evaluation or not. This Viva based evaluation or not. I'll let you know. Okay, but the idea is that you have to keep your things updated in your GitHub repository and keep uploading the work from time to time whenever it is given to you, right? Okay, I'm ending the meeting now. So from the next lecture onwards, we'll be starting with some support vector machine. And what I have mentioned is you have to go through a prerequisite, that is go through Lagrange multiplier once, so that it will be clear when we talk about in the classroom, right? So I'm ending the meeting now.